Okay, so this is going to be CAD lessons in Solidworks. Let's get started. So the first thing you want to do when you're working on a project is create a new file. That's pretty simple. We're going to start with parts, work our way to assemblies, and then talk a little bit about drawings. So let's get started. If you create a new part, you start off in sketch mode. So this menu at the top allows you to create two-dimensional sketches. You will use these to later create three-dimensional contours, features, things, but we're going to start by drawing stuff. So as you can see, I've clicked a line up here, and I need to choose which plane I'm going to be drawing in. So I'm going to just go ahead and choose the right plane here, and then I'm going to hit spacebar and choose this view so that I'm facing perpendicular to the right plane, so everything is nice and simple. I'm going to start by drawing this line. I click at the origin, and now I have to choose a second location to click to create the endpoints of this line segment. So as you can see, I can move around and put it wherever I want. However, if I approach 90 degrees, it'll lock in. So that's how you can assure that the lines you draw are at right angles to each other. If I do this, locked in place. Now I have two locks. I can lock this way at another 90 degrees from the initial starting position, or 180 degrees up here. So I'm going to create a second line segment. When you end a line segment, it will want to start another line segment. So the way I get out of this is I just press escape, and now I have these two line segments. But these do not yet describe anything. I'm going to finish up making this into a rectangle. So if you look, we have our third line. Now you have lots of lining up tools. If you want to go halfway up the Y dimension of the rectangle, it'll lock that in place. If you want to line up with the end of this piece, it'll lock that in place. The dotted lines pretty much explain how everything's working out here. So once again, midpoints, keep in mind that if you lock everything in place the way it needs to be, that saves you a lot of work when you're dimensioning everything later. So now I'm going to finish off this rectangle. Now we have the basic sort of rectangular shape, but there's more stuff you can do. For instance, we have the circle tool. The circle tool, the way this works is you click the center, and then you extend out to describe the radius. So with 2 clicks, that's a circle. Furthermore, if you want to do a rectangle without having to draw 4 line segments, there's a rectangle tool. Click the one corner, click the center, then click a corner, and bam, you have a perfectly described rectangle, easy as can be. So I'm just going to go ahead and delete all these. That's simple. Just highlight all of them and delete. We can go on to some of the other tools here. Polygon, it looks like it's the hexagon tool, but it's actually the polygon tool. So if I want to make a nonagon, this is a 9-sided shape, I enter the number of sides here, and then press check. This makes normal polygons very easy. So I'll click at the origin for the center, and then extend outward, and here I have my nonagon. There are lots of other features here, but I think I've gone over the important ones. You can make whatever these are, slots. You just choose the radius and choose the linear dimensions, like this. Lots of different shapes, but this is most of the important stuff I've gone over. Most of this is self-explanatory. You can look into the rest of the sketching tools later. So I'm just going to next go over dimensioning. Dimensioning is how you make sure that everything is the way it's supposed to be. You have the Smart Dimension tool, which helps us out. So if I click on Smart Dimension, and I click on a line, it will highlight the length of the line, right? So I can choose where I want to put this label. I can choose to label instead the x distance, the y distance, or the actual distance. So I'm going to choose actual distance here because that's usually what's important. And we're going to say, oh, let's set this to 1 inch. Now, if you know anything about regular polygons, you know that this shape is now fully defined. However, say I am not working with a nonagon, and I want to have a shape that's easier to work with. So let's make an actual useful shape, like a hexagon that goes on a bolt head. Now, this is the head of a bolt, but we need to decide what the size of the bolt head is. So the way we do that is with Smart Dimension. You can click here and highlight the diameter of the circle describing the shape, which works. You can highlight the length of the side, or if you click on two parallel opposite sides, you can highlight the distance between the two sides. In this case, that's the same as the inscribed circle, but this maybe will make it a little more clear for someone who's looking at your files later. Either way is okay. You can dimension opposite sides or dimension the inscribed circle. So let's say this is a 7/16 bolt. I don't know what 7/16 is in decimal off the top of my head. However, I can type 7 divided by 16 and press enter, and it'll automatically compute that for me. Furthermore, if you have two lines that you've drawn that are not perpendicular to each other or parallel, you can use Smart Dimension to describe the angle between them. So if I click here, now I'm dimensioning the length of this line. I want this line to be 1 inch, and I want this line to also be 1 inch. But I've accidentally clicked on dimensioning the x dimension, so I'm going to just delete that and try again. We want this to be 1 inch. And now, if you click on one line, click on the second line, you're now deciding on the dimension that they share together, which in this case is the angle. So I can click anywhere where I want the angle to be written. I'm going to click right here, and I'm going to set it to be a 45-degree angle. So using all these tools, you can do a lot of cool things. You can create mirror images by reflecting a sketch over a certain line. That will allow you to save a lot of time. And you can also reflect certain entities. You can do linear sketch patterns, etc. I'm just going over the basics in this tutorial, so I'm just going to stop here with sketching and just basically assume that you can figure the rest of this out. The tools are mostly self-explanatory, so I'm just going to, actually I'm going to keep the sketch, but what I'm going to do is just delete everything and go on to our next little adventure. So now we're going to be working on making a 80-20 triangle. Right, so I start out by drawing a right triangle. I know it's a right triangle because I lined everything up on the 90 degrees. I go over to Smart Dimension, and I type in 2 inches because that is the height of an 80-20 triangle. Go over here, I type 1.5 inches because, oops, I messed up. However, if you mess up, you can just click on a dimension that you want to change, go over to this side menu over here, and right over here, primary value, that shows you the size or the specifications of the dimension. So I can just go ahead and change it to 2. And now we've got our 45, 45, 90 right triangle that we're going to be using to generate this 80-20 triangle. So I'm finished with the sketch. It's fairly simple. The shape is fully defined. So I click Exit Sketch. That's what this icon over here means. And then we're going to go over to the Features menu. The Features menu has the Extruded Boss/Base feature, which we are going to be using to turn this into a three-dimensional thing. So for those of you who don't know, an 80-20 triangle is basically a triangular prism. I happen to know that they're 1 inch wide, so I choose Extrude, I choose the length of the extrusion, which is going to be the width of the triangle in this case, and I click over here on Sketch Selected Contours, and I choose what I'm extruding. So I'm actually turning this triangle into the prism, so I click here, and we have a little projection of what everything's going to look like when we're done. I'm going to go ahead and click the checkbox here, and bada bam bada boom, we have our triangular prism. Now, here's the problem. This is a solid block of aluminum. That's very heavy. So, we're going to need to cut some meat out of this. So what we're going to do that is we're going to start out with, once again, a sketch. Now, here when I click the sketch button, I need to select a plane to draw the sketch on. And now that I'm not working anymore in an empty space, I have to choose a plane on an object. So I'm just going to choose the side plane here. Well, this is not completely arbitrary, but it's anyway. So I'm going to choose this point as the first point of the line. Once again, when you're at 90 degrees, it snaps in place. This is nice. We're going to line it up over here with the beginning point of the previous line and connect it right over there. There's a little line right there that I made by accident. So now we have a right triangle drawn on the face of this. It looks pretty good, but I'm just going to throw some dimensions on there. We're going to dimension the distance between this line and the edge of the face, 1/8 inch. So I just do 1 divided by 8, although it is the same number of characters as 0.1. Actually, it's less characters than 0.125, so we are saving time here. Set the angle here, and now we have a fully defined, I think, thing. So we have this triangle. Now we can't just extrude it here, because then we're gonna end up with like a prism-shaped wedding cake or something. So what we are gonna do here is go back into features, and we're gonna go through extruded cut, which is basically the same as extrude, but it removes material instead of adding it. So extruded cut, we only have one thing, one sketch that we haven't used. So this sketch is so it automatically knows which sketch we are planning on extrude cutting. You can do blind, which cuts in a certain direction. So if I set this to 1/5 of an inch, then it doesn't go all the way through this piece. I'm going to set it to 1 inch because we're going all the way through. Although the best technique is to just go through all, unless you have a reason not to. This means it just keeps cutting until it's through the entire piece, and you're done. This way, if you change the dimensions or specifications of any piece, you have to worry about it. Everything adjusts with it. So it cuts through all. You can flip it, so now it's cutting everything that isn't being intersected by this extrusion, but this is the way we want it. So I'm going to set it back to that. I'm going to press check, and there we go. So now we have this shape. We need to put holes in it, because otherwise how are you going to get bolts in? So if you don't know what you're doing, your first instinct might be to sketch the hole shapes in circles onto the faces of this triangle and just do an extruded cut, which is a reasonable notion. However, Solidworks has a tool called Hole Wizard, which makes things easier. So if you click on Hole Wizard up here, takes a little while to start up, so it's loading right now. You can make holes, but it has a lot of features. So you can countersink, you can do counter bores, you can do threaded holes, slots, all kinds of stuff. We're going to go with the standard just hole. You can choose between all of these specifications. These are like dimensioning specifications here, NC inch, types, all drill sizes. And then you go to hole specifications and you need to specify some information about the hole. So the default here is 1/4 inch, which makes sense because 1/4 is very common use. But say you need an F size or 17/64. It has all sorts of sizes, letter sizes, number sizes. You can add metric and everything. We're going to choose 1/4 inch. And now we just need to decide where the holes go. So I click on positions over here, and it says select a face to put the holes in. So I'm going to select this face, and 1, 2. That's 2 holes. However, these holes are just sitting around randomly, floating in the middle of empty space. So we're going to bring out Smart Dimension to decide where these holes go. You click on the center of the hole, click on the edge, and now you're dimensioning the distance between the center and the edge. It's pretty simple. Most of this stuff is pretty intuitive. Now I'm going to dimension the hole to this edge. Now, here you have a choice. You can either dimension this hole all the way to the edge, or dimension it to this hole. I feel that what's important here is making sure that the 2 holes are the same distance relative to each other. So I'm going to set the dimensions to 1 inch and leave it at that. This way, if I ever change this 1/2 inch, this will automatically adjust so that it's still 1 inch away. This may not come into play because 80-20 triangles do not change. However, it's important to future-proof your stuff in case you change it later on. So now I'm going to do Hole Wizard again. Just pop some holes in. However, this time, line it up. So I hovered over the midpoint of this line, and now it tells me when I'm lined up with this midpoint, which is going to save me time dimensioning later. So pop it down. Now, once again, blue dotted line tells us we're lined up, and we know that these holes are already centered, so that's 2 less dimensions we have to do, 1 for each of these holes. So, time saving. Check, check. There we go. Now, I seem to have forgotten to make these holes through all because I was distracted. I'm going to... No, I did this on purpose so I could show you how to use Edit Feature. So, over here on the left, you have a chart that describes everything that you're working on. So in this case, all of the features of this part. So as you mouse over each one, it highlights that feature. So I'm going to go to this hole, right click, and you can use Edit Feature to go back into the menu where you're setting it up. So I don't have to change positions, but what I want to do is change the end condition, which shows when do I stop drilling. I'm just going to do through all, or done with it. So this allows you to change things that you messed up or just, need to change. So there we go. We have our 80-20 triangle. They normally have a little bit more clearance over here where the holes intersect, but that is not important right now, so we're not going to worry about it. One thing that we are going to worry about is fillets. If you've ever seen an 80-20 triangle, you know that they're rounded on the edges. So I'm going to round the edges. Now, there are many ways that you might think of doing this, but there's a tool called Fillet, which just decides this. You choose items to fillet. Choose the line that you want to fillet. I think you can tag on. Yeah, we tagged on both of those lines because they're both going to get filleted. And then we need to choose the radius of the fillet. So we're going to put it into 1/4 of an inch. I don't know what it is in actuality, but that seems like it could be right. Press check. That was way too large. Make it 1/8 of an inch. There we go. That is more than the actual fillet on an 80-20 triangle, but I don't care. So now we have an 80-20 triangle. Save it with Control S. That's pretty simple. We're going to call it 80-20 triangle. Oh, I already have a file called 80-20 triangle. We're just going to call it that. The file type for SolidWorks is, the part type is .solidpart. That's SLD part. So if we close this now, we can open it up later. File open, that's self-explanatory. However, what if you want to make a thing that's not a prism? That's a problem. We don't know how to do that. So I'm now going to go over some of the basics of making non-prismical things. What we're actually going to do here is make a ball for us to play with, but not really, because it's digital. So obviously, if you're making a sphere, which is what a ball is, you start with a circle. So center, radius, smart dimension. Now we click on the circumference of the circle and asks you to dimension the diameter. This ball is going to be 24 inches long. It's 2 foot. It's a yoga ball, or a 2014 game piece. And now we're going to draw a line going through the diameter of the ball. And the reason we're doing this, it will become apparent later, but we need to reference this. You'll see right now. So I finished this simple sketch of a circle with a line going through it, and now instead of extruding, you do revolved boss/base. So if I click revolved, and then axis of revolution is the first parameter here. So this is the axis that you're spinning around. This is similar to extruding, but instead of sliding directly through a dimension, you're spinning about an axis. So select the axis, then select the contour. So we're just going to choose half the circle, and direction, you could do all these things. I'm just going to do blind 360 degrees and hit the check button. Hope it works. Can we just thickness 0? Can we do that? Can we just get rid of this? Why isn't this going? Okay. What did I forget here? Yeah, I'm just pressing random things. Resultant contour intersects the center line. Oh, I can just turn this off. I don't know what that was. I could look it up, but it looks irrelevant. So I just turned that off. Click check. Bada bam, bada boom. It's a ball. We did it. You have extruded. What was it? There's a revolved cut. Revolved cut here works the same as revolved thing. Works just the same. You can revolve around a line that is outside of the sketch, or outside of your contour. So if I want to edit feature here, I can edit the thing. So if I want to make this into Pac-Man, 270 degrees. It's not really Pac-Man, but it kind of looks like Pac-Man. So you can change how much you're revolving it. You can choose an axis of revolution that's anywhere in the sketch, but it has to be part of the same sketch, so you can't just revolve around some line in another part sketch. That's enough about parts. Obviously, there are many more features, once again, but I don't feel like going into them, because this is a basic lesson. So we're going to now move on to assemblies. Okay, so now we're going to move on to assemblies. Assemblies are basically systems with multiple parts in them. So the way we're going to do this is we're going to make an assembly out of multiple of these 80-20 triangles that we've made here. So once again, new, you want to create a new file, new assembly, press OK, and you start with an assembly. So the first thing it's going to do is ask you to add a part. One important thing to note is that the part you put down is going to be static by default. So what this means is that this part doesn't move. Everything else moves relative to this part. So you want to have something relevant as the first part. But it's actually not necessary, because the theory of relativity says you can do whatever you want. So now that we have this 80-20 triangle in place, let's insert another 80-20 triangle. So you can click up here, insert components, and choose another 80-20 triangle. If I click here, it's going to put the 80-20 triangle in and close this menu. Say I wanted to add 5 80-20 triangles though. I don't want to have to open the menu a bunch of times. So open this up, click on this little pin here, choose your part. This menu will always have all of the parts that you have open. You can also add assemblies to your assembly. If you want to put in an assembly or a part that is not currently open in another window, browse, choose the part, you're done. So I'm done here. I'm going to press check. I'm going to get rid of a bunch of these 80-20 triangles that I don't need. Now I'm going to start showing you guys how to attach things together. So the basic way you do this is with mates. Here I have a mate icon button, right? So mating is where you define the two elements of two different parts together. You define how they relate to each other. So I'm going to choose this face here and this face over here. And now they are set coplanar. So this means that no matter how I move this piece, it will always be coplanar to that piece. But there's another way they can be coplanar. It's that they're facing each other. Right, so now we have their coplanar flush, but you can flip them around. And the way you do that is you go over here, and you choose the mate alignment. So I can choose this mate alignment where they're facing against each other, or this mate alignment where the two pieces are flush. I'm going to choose this one. So now we have two pieces that are facing directly against each other, like this. However, they can still move around. So, once again, mate. Your mate window stays open after you make a mate, so the next mate we're going to make is this face to this face. Just keep them coplanar. And the final mate we're going to make is this one, this face here to that face there. So now we have these two 80-20 triangles that are perfectly lined up against each other. However, there are other ways to mate objects together. So I'm just going to go into the menu here, delete all the mates we just made, and go over some of the different kinds of mates that you can do. So the first thing I'm going to do now is a distance mate. So say I want these two pieces to face each other, this one and that one, but I don't want them to be right up against each other. If you go down here and you click this little distance icon, now you can choose the distance between them. So make them 1/2 inch apart, and now you have two 80-20 triangles that are a fixed distance apart from each other. Once again, they can still move around, but this distance in this gap here is always going to be the same. So, while sometimes it looks like you've maybe moved them so that they are not the same distance apart, that's just a trick of perspective, because unless you have a 3D computer screen, there's only so much you can do. So, once again, if I just do mates here, like that, now this only slides in one dimension. Now, here I have the lucky situation of being able to mate these two edges together, or these two faces, like this. However, what I can also do is mate these two edges over here. So, you're not constrained. Well, I could mate them if they weren't a fixed distance apart. So, that actually doesn't work here. So, I'm not going to do that. But you get what I was trying to say, right? You can mate edges together. Now, we saw this problem, and say I had filleted this edge as well. Well, I'd still be able to line this up by mating the planes together, but for the sake of argument, say I couldn't do that. I can mate these circles together, which is how it actually ends up on the robot, because you're mating holes together by sticking a bolt through. So I mate these two holes together, lines up. These two holes are now concentric, so that means they describe the same infinitely tall prism in space. So that's another way to stick two things together. Now, there are other kinds of mates that you can do. Just going to go back in, delete the mates again. I'm going to go and mate these two filleted edges. So the default mate here is concentric, so that they describe the same circle, which is interesting because, you know, this is cool. However, that's not a realistic usage, so I'm going to undo that, and this time I'm going to mate them as tangent. So you can either click on this edges and then click tangent, or click on tangent and then click on the edges. So now these two circles are tangent to each other, so they'll always stay in contact. You can mate edges to each other like this, so that they rotate but stay with edges in contact. And there are lots of different ways that you can mate things together. Now keep in mind, I cannot move this triangle, because this triangle describes the origin of the entire assembly. So there's no moving it, even though I can move this one. Everything in the assembly is described relative to its location, based on the origin of this part being the origin of the entire assembly. So that's the basic idea behind putting things together to make assemblies. It's important to keep in mind that many parts you don't need to CAD yourself. You can download the CAD for most gearboxes, for instance, online, and just import them into your assemblies. You can use assemblies inside of assemblies. So if you download an assembly describing a gearbox, then you can import that into a separate assembly, maybe a robot assembly. It's a good idea to have each subsystem of your robot be part of its own assembly, so that you can change one and someone else can work on a different one, and you won't create any sort of version issues. So I'm just going to hit save, rebuild and save the document. Rebuilding is basically re-rendering your assembly. So Solidworks has some optimization that allows it to not take a million years every time you change a little small thing to re-render all of what you've done. However, sometimes this will create small issues where objects that you've already deleted still appear, etc. So it's a good idea before you save to just rebuild your document. However, if you're running low on RAM, you might want to save it without rebuilding and then try and rebuild it, because sometimes rebuilding can crash your computer if you're not in a good spot. So the manual rebuild, right up here. Just click and it rebuilds. So in this case, super fast because this is a very simple assembly. So I'm going to go ahead and close this assembly, and we're going to move on to the next thing. Okay, so the next thing that we're going to be talking about is finite element analysis. This is basically where you test how a part reacts to being put under various forces. And, does your part break? How much does it bend? Etc. So here we have a simple L that we're going to be using to show how this works. In this case, I just made this very quickly. So this is used no new techniques from earlier in this video. So that means that it has no designated material. We'll fix that later. And it's basically 1/8 inch thick aluminum, 1 inch wide, 3 inches long on each of the legs of the L. So we're gonna open up Simulation Express, which is the built-in SolidWorks finite element analysis program. Click right here. This is a Tools Simulation Express. It basically guides you through the entire process. So, here's the introduction. You can read this. I'm not going to. Press Next. The first thing you need to do is fixtures. So basically, a fixture is the part of your part that doesn't move. It's fixed in place. So I'm going to choose to add a fixture. Now I'm just going to fix this entire plane right here. So basically, however you mount this piece, you want to fix that part of its geometry. So if you have 2 holes, for instance, that you're putting bolts through, well, that's where it's fixed, right? So you want to fix the holes. There are no holes here. You cannot run finite element analysis on assemblies. So each individual part, you basically just fix the point or plane where it's attached to another part. So the best representation of this in reality would be like some super strong Velcro holding this to another piece, right? Because it's being fixed along this plane. So pretty much impossible to pull off in real life, but it's good enough for our demonstration. Once again, like however you are mounting it, you want to fix the part that you're mounting. So once you click add a fixture, I can add another fixture. Just click add a fixture again, but I'm not going to. I'm going to go on to next. Loads, so you can add forces and pressures. I'm not going to go into detail about how this works, what the difference is between them. I may link a tutorial on a more in-depth tutorial on finite element analysis that can show how some of this works and some of the physics behind it. But anyway, so I'm going to click here to apply force to this surface, let's say, and we're going to change the magnitude of the force, right? So because first uses all English units, we're going to go ahead and use English units. So that means this is measured in pounds of force, right? So I'm going to just make it 30 pounds of force, right? Obviously, you can use newtons if you want to. Just change the unit to SI. Go ahead and check that off, move on to the next step. So the next step is material. So we have to choose a material. The most common alloy that we use, on our team at least, is 6061 T6 aluminum. So I'm going to go ahead and make this out of that. And just click here. Note that when you click apply, it doesn't automatically close the window. So you may feel like, oh, it's not working. No, it's working. You just gotta close the window. And as you can see, I close it. We have, ta-da, the specs of the material, right? So this is some of the specs of the material. You get Young's modulus and yield strength. Not gonna go into detail about those. Once again, if you mess up, change material. Easy. Next step. So it just tells you you're ready to go. I'm gonna click run simulation, and it's going to run the simulation. On more complex parts, this can sometimes take a while, but this is pretty simple, so it should be pretty quick. So now what we're looking at is a animation of what's happening to the part as this force is applied, right? So this is pretty much what we're expecting. When you apply force onto this L, you expect it to bend. It's important to note, however, that the animation is often exaggerated so that you'll be able to see it. So maybe if I put 1 pound of force, it would still give the same animation, even though that amount of force in real life would not be enough to bend this piece. So it does that because this way, if you, even if you can't see it, you're making sure that everything is basically getting evaluated properly. This is the insanity check to make sure, because the computer doesn't have any common sense. So if you messed up and things are not bending the way you want them to, because of, most likely you forgot to add a fixture somewhere, then you can just change it. So, this is basically double check. Don't freak out if your part is bending like crazy. It's supposed to do that so that you can clearly see what's going on. I'm going to, and then it asks you, is everything as expected? So if you've messed up, you click no, return to loads and fixtures. If you haven't messed up, go ahead and click yes, and you can look at the stats. So now you have basically two things here. Von Mises stress basically shows what parts of this material are under the most stress. So von Mises stress, everything is laid out here, color coded, and then the key is over here. You can look, so at this red point where it's taking the most stress, you have 1.184 times 10 to the 8th newtons per meter squared. And if you look down here, the yield strength of 6061 T6 aluminum is 2.75 times 10 to the 8th. So when you reach 2.75 times 10 to the 8th, your part will permanently deform. So you never want to hit that, and you want to stay very clear of this. So we're getting like a third of the way there. Not really. Yeah, like a third of the way there. So we're probably in the safety zone, putting 30 pounds of force along this surface here. Different results if you put 30 pounds of force right on the end, but that's a different simulation. So now we can show displacement, and we go, okay, so because we're within a safe margin here, we know that this piece is not going to permanently deform. However, we want to know how much it's going to bend when it's taking all of this force. You click on show displacement. This is measured in millimeters. If you tweak your settings, you can probably get it to measure in inches. I think I had it in inches before, but for whatever reason. So this is to be expected. The points furthest away from the fixture are moving the most. So you expect that on the end it's going to move 1.447 millimeters. So that's how this all looks. You can basically, when you're done, well, yeah, you can actually play the animation that shows, everything with the color-coded forces, and you can stop, switch to stress, play animation again, and it shows where all the stresses are. So I'm going to go ahead and click done. You can generate a report or an eDrawings file, which basically store the output of your test. That's all for finite element analysis, I guess. So, if you're done, next. And yeah, we're done. Okay, so we've arrived at the last leg of our journey. We're going to be going over creating drawings for your parts. So basically, a drawing is it's a drawing of your part, but I mean, that was obvious. So drawing is basically a two-dimensional representation of what your part is, so that someone who maybe doesn't know CAD or doesn't have a computer with them will be able to create your part without the need of a computer. So, it's a printable two-dimensional representation of your part. So we're going to go ahead and click New, Drawing, OK, and then we're creating a new drawing. We have a multitude of options here, but we're going to just go ahead and go with the default. These are different formats, as you can see. They have to do with the size of the title block at the bottom, orientation, portrait, or landscape. You can look into which ones you want to use when, but for now, we're just going to go with the default. Okay, so our drawing says it needs a document. It needs a file that you're going to be representing. So here we have this file open, so we're just going to double click it and choose it. Right, so now we want to put in the different views. So we have the square representing how much space this view is going to take up. This is the front view. So you can put it right here or wherever you want. Of course, depending on the way you've arranged your piece, it may look different. So that's the top view, that's the side view, and there's the isometric. So once you put all your views in, of course you can do like side other way, etc., however you want, but I'm not going to do that right now because we have all of the information that we need. So I'm going to go ahead and click the checkbox and start looking at our drawing. Now you can't look at this in 3 dimensions anymore because now you're looking at a 2-dimensional representation, but you can use Smart Dimension to add smart dimensions. So if I want to define the length of this piece, I can do the length from this line to this line, right? Which really should be 2 inches unless I messed up somewhere, but we're just going to assume that I messed up somewhere, right? Right, yeah, we're just going to assume that I messed up somewhere. So we have a dimension here. We want to create more dimensions, right? So we're going to put this dimension in here. You just click on the line. It's very similar to putting dimensions into your sketches and your assemblies. However, you don't actually change anything when you're adding information here. So this is just visual representations, As you can see, I have lots of stuff going. If I label this, it says 0.25, but say I want it to say quarter inch hole. Well, what I can do to do that is do a annotation note and just add a note to the circle and make it say, quarter inch hole. You can change the font size, etc. to whatever you want. So now we have this labeled. You get another copy of the label, so if I want to label a bunch of holes with the same thing, I can do that. Right, so it just saves basically the text of your label in case you want to make more labels that are the same. So we have labels there. You can label our fillets, for instance. For that, you want to just go back to Smart Dimension. That'll make everything easier. Click here, and it tells you the radius of the fillet, which is the pertinent dimension here. So for the most part, it's going to basically give you the dimensions that you need. If you look at, if you just Smart Dimension it, Smart Dimension is a great tool. You can dimension all the things, very convenient. Right, so I just, spam the dimensions here, and now say I'm ready to give this to my machinist. Well, I'll go ahead and save this document. I'm going to save it as, the part name that I will not attempt to pronounce, .solid_drawing. Right, so I can do that. But say I'm giving it to someone who doesn't have Solidworks. Or maybe I need to port this to a computer that doesn't have Solidworks, a personal computer maybe. So I can use save as, change the file type to any sort of thing, JPEG, PDF, whatever. I'm going to do PDF. Save that, and so now we have a PDF version of this, which you can open up and print. You can also just Control P to print everything. Just print it directly. So if you're printing off of the same computer that you do CAD with, fantastic. That saves you time. So I'm going to go ahead and close this, and I'm just going to, before we go, talk a little bit about hotkeys. So throughout this CAD lesson, I've been using the buttons up at the top window. However, there's a much better way to do things, and that's with hotkeys. So if you want to change how you access different things, well, first of all, you have default hotkeys. L is for line, B is for build, I think, rebuild. I don't actually know the default hotkeys because I don't use them. However, you can go into Tools, Customize, and Keyboard. And then you can go through all of your keyboard shortcuts and make things a lot faster. Keyboard shortcuts will just save you a ton of time, especially once you get used to them. Personally, the keyboard shortcuts I use is Q is for Smart Dimension, W is for line, E is for rectangle, R is for circle. So this means that when I'm working in sketches, I have all of my basic sketch functions on the QWER keys, so that I can access them without having to move my left hand basically at all. Next, I have Smart Dimension, once again bound to A. You can have multiple keys bound to the same function. Extrude bound to S. Extruded Cut bound to D. And Hole Wizard bound to F. So this means that when I'm working in the part context, I have all of my basic extrude, cut, hole wizard functions bound once again to these the home row 4 keys, ASDF. and that way I don't have to move my fingers around when I'm working in the part context. Finally, Z, once again, smart dimension. X is bound to mate. C is bound to measure. Oh, that's a thing I didn't go over. Press C. It's like smart dimension, but it measures things and doesn't actually change dimensions. Yeah, so C is for measure, and this means that when I'm working in the assembly context, I have my basic functions. Once again, I have smart dimension on my pinky at all times, so this has allowed me to optimize my workflow a lot, and I'm trying to get these to become the team hotkeys. I highly recommend one of the first things you do when you're working with Solidworks is just bind your hotkeys, because the sooner you start getting used to them, the better. And also remember that the best thing you can do to get better at CAD is just practice. Just make things in CAD and you will get better at it over time. So, even if you don't have something specifically that you need to build, you can CAD a hypothetical robot, just for practice, as a design exercise. As you do this, you will get faster and faster, I promise. So that's all. Maybe more in-depth tutorials coming later, but probably not, because I don't want to. So, yeah.